Hello and welcome to the last question we're doing. Choose your fighter. What sort is the best to use and why? So basically these questions are just some kind of conceptual questions on sorting, and hopefully after going everything we did in the previous two videos, these will seem relatively straightforward, or at least it will make sense why they are the way they are. Okay, so the first thing is you have a system running in search and sort, and we find it's completing faster than expected. What could we include about the input to the algorithm? So the best case of insertion sort is n, and the worst case is n squared. So if we are running a lot closer to n than we are n squared, we can assume that we have data that is very close to, if not exactly, the best case for insertion sort. What is the best case for insertion sort? The best case is when the data is already sorted. So we can assume that the data is mostly sorted already. Right, so if the data is already mostly sorted, then insertion sort is probably going to end up actually being your fastest sort. It's going to run close to this n. Of course, generally speaking, we can't really assume anything about our data. So if we don't know anything, we can't make this decision. But if we do know that it's mostly sorted already, we can then use insertion sort. Okay, and then this is kind of related to the previous one. The second one is give a 5-element array that gives the worst case for insertion sort. Well, if already sorted gives us the best case, not sorted is going to give us the worst case. And in particular, we talked about this a bit in the previous video, but a completely backwards array is going to give us the worst case runtime, because we're going to have to do a swap here, then here, swap here, then here, then here, and a swap here, then here, then here, then here. And that's going to give us our worst case runtime. Okay, some reasons you would use merge sort over quicksort. One is quicksort need not be stable. It's not guaranteed to be stable. The version, I talked about this earlier in the videos. You could implement it such that it is stable, but in order to do that, you have to make sure you specifically say, okay, in the case of ties, we keep things basically on the side they already were. If you do not do that, which many implementations, most implementations of quicksort are not going to do, it is not stable. So if it's not stable, you're not going to use it over merge sort if you need stability. So the main time you need stability is when you need to do multiple sorts on a single set of data. So that's one reason you would use merge sort. It's going to be faster in many cases. The other thing is that the merge sort has a best case and worst case of n log n, whereas quicksort has a worst case of n squared. So if you know that you're sorting data that is going to generate a worst case, or the case that is near the worst of quicksort, then maybe it would be better to use merge sort. What is the worst case of quicksort? It is the case where the data is already sorted either forwards or backwards, in reverse or the right way around. Notice, just as kind of a funny thing, that the worst case of quicksort is actually the best case of insertion sort. And the worst case of insertion sort is also the worst case of quicksort. Kind of weird like that. But anyways, so if you know you're going to generate something closer to the worst case, you would do it. One thing to note, though, in general, is that quicksort out of the comparison-based sorts is generally the fastest sort, because the reality is quicksort runs a lot closer to this n log n than it does the n a lot of times. Okay, which sorts never compare the same two elements twice? So that's going to be quicksort, that's going to be merge sort, and that's going to be insertion sort. That's not how you spell insertion, but you get the idea. So quicksort is not going to compare the same two elements twice, because remember, we always compare every element to a pivot, right, linearly. We pick a pivot and then we compare every element to that pivot one time. And once we're done with that pivot, we never use it again because it's sorted at that point. We move on to another pivot. So you're never going to compare the same two elements. Merge sort is going to be kind of similar in that we're going to break everything up into subarrays, and then we're going to combine elements of the subarray, but we're never going to need to compare the same elements of the same subarray over and over again. Why is that the case? Because if you remember the earlier example I did above, we started out by comparing elements from one array to elements in another array, right? We compared 1 to 0, and then we compared 4 to 1, and then 4 to 2, et cetera, et cetera. Well, after that run, after that merge, this is going to be sorted. So we're going to have 1, 2, 4, and we're never going to need to compare elements within the same subarray to each other again, right? We're always going to be comparing them to a different subarray of size 4 somewhere else. So we're never going to compare elements of the same subarray to each other. Okay, and then the ones that do are going to be heap sort, because when you do bubbling up and bubbling down or sinking and swimming, sometimes you compare redundant elements a lot. If you remember when I did the heap sort example above, I would end up with 1 or 2 on top of my max heap a lot and have to bubble things down really often. That kind of thing can happen a number of times over. And then selection sort, you might need to compare this. You'll need to compare the same elements over and over again, because that's what you're doing in selection sort. You're scanning through the array and then you're saying, okay, which is the smallest? So you have to compare all these elements that you scan through a subarray, say which is the smallest. So you're going to do a lot of redundant comparisons like that. This is the answers given on the worksheet. If you want to be a smartass about it, you could also say counting sort, LSD and MSD, because these sorts don't do any comparisons. So they certainly don't compare the same 2 elements twice. That's a bit of a technicality, but you could also write that if you really wanted to. Okay, when would you decide to use a radix sort over a comparison sort, and vice versa? So in general, if you can use a radix sort, you probably would want to, because radix sorts are the fastest sorts in general. If you look up here at this table, it's a little tricky, because you'll notice that the radix sorts have different terms in them that the other sorts don't have. It has the L and it has the R term, but generally L and R are going to be relatively small numbers. And we would generally still say that all these non-comparison based sorts are going to be linear in runtime. And if you look at all of the comparison based sorts, the best case you could possibly get for any one of them is linear, and most of them are going to run in n log n generically, right? So linear is better than n log n. So in general, if you can use a radix sort, you would probably want to use it because it's faster. One reason that you wouldn't want to use it though is, as we talked about when we were doing radix sorts, you need to have a very clearly defined radix. You need to have everything be very sortable based off that radix. In other words, there's a lot of kind of setup and necessary preconditions that you might need in order to make this work. So these generic sorts are more robust. They'll work for different types of objects that might be comparable, but might not necessarily fit into the common mold of either numbers or letters, which are the most common radix things you would sort on. So they're going to be more robust than radix sorts. Is the main reason you would want to end up using them. Okay, one final note I want to do about this with this is I want to ask the question, looking at this quickly. So notice that we have something here. Notice we have like quicksort here has a best case of n log n, and has a worst case of n squared. And then notice that insertion sort has a best case of n and it has a worst case of n squared. So here's the question. Why would you ever use quicksort? Because it looks like the insertion sort best case is only better, and insertion sort can't get any worse than quicksort, right? They run equally poorly in the worst case, but insertion sort runs better in the best case. So why would you ever even use quicksort? Well, the reality is that asymptotics are not everything. Asymptotics don't always matter, right? Because what ends up happening is insertion sort, you end up running a lot closer to this n squared in the real world than you do this n, and in quicksort, you end up running a lot closer to this n log n than you do to this n squared, right? You can think about that just because of how the different best cases are generated, right? The insertion sort best case is generated when everything is already sorted. You're probably not, most of the data you're randomly getting is probably not already sorted. And quicksort runs best when everything is kind of randomly distributed, right? So that you can split the data in half every time, which is a much more common occurrence. So that's one thing to keep in mind about all sorting algorithms and all algorithms in general is it's great if the best case is this, it's great if the worst case is this, whatever, but the real world runtimes are often not very reflective of the best and worst case. So I know that we get rid of constants, we say they don't matter, we say small terms don't matter in runtime, but the reality is they do when you're actually running on your computer. So that's something to keep in mind. Okay, that is this question. I'm not going to do the final one because it's an algorithm design question, which is not in scope, but you can do it if you want to. And thank you for following me on this journey of doing these 12 worksheets over the course of the summer. I hope you enjoyed this, and I hope this was somewhat helpful.